Okay, this is part the example of level spills plot, where we call this as level spills plot, where FA naught over negative RA versus you need to plot FA naught over negative RA versus X. This is level spill plot. So the next step is for your test, if you are given with this information where you need to use level spill plot. Okay, so that means you need to have FA naught. You need to know what is the value of FA naught. In this case, species A enters reactor at a molar flow rate of 4 mole per second. So enters, okay, enters. So this is the initial flow, which in other words is our FA naught. So in the question, if you are given with this kind of information, so you need to know that this is the information for FA naught. Then calculate the volume necessary to achieve 80% conversion. So 80% conversion, if you plot this graph, you will use 0 to 1, or you can also use 0 to 100. If 0 to 1 means 80% is at 0.8. 0.8. Okay, if you use 0 to 100, which means this is your 80%. So it depends on the question. If the information given in the question is in term of the number, okay, from 0 to 1, okay, so you just plot uh, using this number. You don't have to convert to percentage. Okay, and then this is to show the difference between CSR and also PFR. So this is clearly show us that the volume for CSR is greater than PFR at 80% conversion for this kind of curve. Okay. And next, this is for parallel reaction, where we have a desired product and also unwanted product. So from A, our desired product is R, unwanted product is S. Okay, but we need to consider both, because this one is the constant, okay, rate constant for R, for A to R. K2 is rate constant for A to S. So if we write this in terms of the rate of reaction, we will have dCr over dt equals K1 because belongs to this part, right? Because we want to progress R. So dCr over dt equals K1 Ca A1. But for RS, we have dCs over dt equals K2, because this part, okay, K2 produce S, so dCs over dt equals K2 Ca to the power of A2. And then we can simplify this. We can divide both equation. Okay, this is equation number 1, equation number 2. 1 over 2, we will have this. Okay, just copy back everything here. But this one we can simplify and make it as A1 minus A2, because CA to the power of A1 over CA to the power of A2, we have learned during our secondary school. Anything that is involving power, okay, we can simplify it as long as it is the same. This is the concentration A, the same constant, I mean. So we can do like this, A1 minus A2. Okay, that's why we got this part. Okay, CA, CB both high. For this is our first situation, second situation, and third situation. Okay, this is the contacting pattern. We call this as contacting pattern. So if we can mix both together rapidly, or we can mix them slowly together. Okay, this both first and second is together, but the first one is rapidly, the second one is slowly. But the third one is we can have this kind of contacting pattern where we put one. For instance, this one A is already inside the beaker, and then we insert B slowly, or it can be in other way, B A. depends. Okay, so we can put B first, then A we insert it slowly inside the beaker. So this, all of this we call it as contacting patterns. So various combination of high and low concentration of reactant in non-continuous operation. Non-continuous because this is batch reactor, right? Batch reactor or semi-batch, either one. Okay, next, based on the contacting pattern that we have learned, this is one case study to show the product distribution with respect to contacting pattern, where we have two reactions here. First reaction, second reaction. Then if you realize A react with B, produce R, have K1 as the constant, and then here B is the intermediate, R is the intermediate product where it will be react back with B. So in other words, we can say that B is in excess, okay, because we have more B than A. That's why B can react with R back, and then it will give another product. So here we have intermediate product, intermediate product. Okay, so we can say that B is in excess. A is, we call it as limiting reactant. It is limit, right? B is more than A, so limiting reactant. So case 1, add A solely to B. A is limiting reactant, right? So A is limiting reactant. Limiting reactant add to um, in excess. B is in excess. So limiting reactant add to excess reactant. So it will give, because this will consume all A, because A is limited. Okay, the mixture with very high concentration in S can be found. So we can have this high concentration of S if B is inside the beaker and A is added slowly inside the beaker. And then we have second case, add B slowly. B is in excess and then A is limited. So anything that is in excess added to limited reactant, which is in the beaker for this case, concentration of R will be built up inside. So R will be built up. We have excess B and then A. R will be built up inside the beaker. After reaching a maximum, R will convert into S, and the process will be gradual. Okay, then we have the third case, add A and B rapidly. Both to we add rapidly in the beaker, give the behavior of series of reactions. So this reaction will happen simultaneously. It will react together at the same time. R will increase first, and after reaching maximum, it will diminish, and concentration of S will increase. Okay, so in other words, this is to show us that contacting pattern is very important in designing a reactor, because we need to consider the time consumed, and how to optimize the process if time is very limited. Okay, so that's why contacting pattern is very important in designing a reactor. This is for multiple reaction. Okay, in multiple reaction reactor design, contacting pattern is most important for factor to get a particular product. In irreversible reaction in series, so we have A produce R, and then R produce S, so we have K1 and K2 here. This is considered as different chain of reaction. So the mixing of different composition is the key to formation of intermediate. So this is our intermediate. 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 Okay, the mixing of fluid of different composition is the key to formation of intermediate. The maximum possible amount of intermediate is obtained if fluid of different composition and different stage of this is not conversion, okay, conversion. Conversion. We are not talking with this reaction. Okay, and different stage of conversion are not allowed to mix. In series of reaction, if intermediate reactant is our desired product, then semi-batch reactor will be used. If intermediate reactant is our desired product, in other words, if this is our desired product, okay, So semi-batch reactor is preferred. Okay. And then for catalytic reactor selection parameter and design, we need to consider the reactor type, okay, CSCR, PFR, okay, and so on, okay, etc. Okay, and then reaction type, okay, and then rate of reactivation, economics, other process requirements. So these five are very important for catalytic reactor uh, parameter and design. Okay, reaction type. If we go to the reaction type, because we have five parameters here, so we go to reaction type. Chemical kinetic of reaction can be known by knowing the type of reaction. Okay, so reaction type and reactor type, reaction type. Okay, so where we know that the kinetic uh, we just want to tell you that reaction is different as compared to reactor. Reactor is the container that we use. Reaction is what is the reaction between the reactants. Okay, what kind of reaction? Okay, so chemical kinetic of reaction can be known by knowing the type of reaction. For reactor selection, reaction type will tell us about heat of reaction. Either reaction is endothermic or exothermic. Selectivity is defined as reaction rate ratio for two parallel reactions. Catalysts are used to increase reaction rate and selectivity for a specific reaction. So catalyst is very important to increase the reaction rate if time is our problem. Catalyst can be used. We can determine what type of catalyst need to be used. Okay, sorry. Okay. We can determine what type of catalyst need to be used. Reaction temperature range also need to be determined. So T is important. Okay. So for reaction type, we need to consider T, and then we need to consider R. Okay, rate of reaction, and so on. Okay. For reactor type, reactor may be a plug flow, mixed flow. Okay, mixed flow is CSCR again. Okay. So when we talk about CSCR, normally we will have impeller, right? Stirrer, impeller. So your next step is to study about impeller, type of impeller, the type of flow. If different impeller have different type of flow, so you need to know that. Okay, to study that for your test. Um, Batch flow reactor or other contacting pattern. Okay. Uh, and then a reaction conductivity of reaction need to be determined. We also have learned about this previously in previous video. In case of expensive catalyst and high heat transfer rate required, mixed flow fluidized reactor are used. For high mass transfer, plug flow reactor will be used. Okay, so expensive catalyst and high heat transfer rate, so we will use mixed flow or fluidized bed reactor. High mass transfer, okay, plug flow or packed bed reactor will be used. Okay, so in other words, your next step is for your test is you need to know how to relate what is the relationship between chemical reaction and also reactor type or reactor design. What is the importance of chemical reaction in designing the reactor? So you need to know the important points behind that. Okay. Last but not least, for economics, okay, instead of using different size of mixed flow reactor in series, equal size mixed flow reactor are economically good. So we need to use equal size, okay, instead of different size. If catalyst is not expensive, consider non-regeneration. If expensive, regeneration must be considered. So in other words, this both of this situation will determine the rate of reaction of the process. So you need to, for your final tip for your test 2 is you need to learn about rate of reaction. Okay, question related to rate of reaction will be asked to you. Last but not least, please give feedback. Go to menti.com. 68431625 is the code, and then please give feedback regarding this course. I would like to say sorry if I have made mistake or my explanation is not that good, and then you have a difficulty in understanding my explanation. But from first week to week 14, I hope that you will be happy with what we have learned. hope to see you next semester. Assalamualaikum warahmatullahi wabarakatuh. Take care everyone.